All right. So before I start, just a few things. For the open access for the lab, like I said, I will update you weekly. So for this week, there is no open access available because EVP1 is fully using it. Right. So the only slot available is our Friday lab slot. Okay, but next week, the EVP1 is fully online. Okay, so next week, basically Monday to Thursday, if you need to come to the DSA lab to do any soldering or prototyping, you are free to do so. Okay, just come in and you just tell Uncle Jalil that you are from 2271. Okay, and you need to do some soldering or some work, he will let you in. All right, so next week, Monday to Thursday, you can come in and you can use the lab facilities if you need. Okay, but this week, the only slot is our Friday lab slot. Okay, so every week I'll update you, okay, based on the plan of EPP1. All right. Okay, so let's get started. So this topic is on exceptions and interrupts. Okay, so exceptions and interrupts are basically things that you have already sort of learned before. All right, and this set of slides, I know some of you may already have access to slides from previous batch of students and so on. Okay, so in the previous batch, this slides was twice this length because the first half we went through in very detail the entire ARM processor's behavior during interrupt. Okay, but then I think it was a bit too much and probably best left to another module. So I've taken out that portion and focused more on the application side of it. All right, so those details on the ARMs handling in terms of the stack, what gets pushed, what gets pops, and so on. All those stuff, I think you will learn more in another ARM focused module. So here we are going to, I've taken out that content and I've just focused on the exception handling and how to apply it to our controller over here. Okay. So let's come back to the idea of interrupts. Okay. So if I give you back this scenario of switch and LEDs, a very simple example, we definitely know how to do this, all right, in terms of polling, correct? We can check for the switch to be pressed, and when the switch is pressed, when we detect it, we are able to control the LEDs. Okay, and this is basically what you sort of know, okay, quite easily. So over here, if you recall this switch here, as you can see, it is by default active high. Okay, by default it is active high, it's 1. All right, because it is pulled up here, when I press the switch, okay, when this switch is closed, it will go low. Okay, when I release, it will go up again. Okay, so this is what we call an active low switch, okay, which we saw last week. And these LEDs are also active low LEDs, correct? Because you need to apply a 0, then the current will flow and the LED will light up. Okay, so these are just configurations that you can tweak. Okay, so in our case, of course, the RGB LED, you can't do anything because it's fixed on the board. Okay, but if you're doing your own design, you're free to do anything that you like. Okay, in terms of switch, we are going to be adding the external switch in this week's lab. Okay, so that is why you have a switch given to you in your kit. All right. Okay, so before we get on to that, let's just make sure that your GPIO concepts are intact. All right, so I'm going to launch a poll now, okay, to see whether you remember your GPIO concepts. Okay, so you can see 2 questions there. You probably need to refer back to the data sheet. Okay, if you remember, I told you the data sheet is something you need to use very regularly, okay, in our course. So please always have that on standby, okay, during our lectures and labs and tutorials. Okay, so I give you a few minutes, look at these 2 questions and submit your answers. You don't need to rush. Look back at your data sheet. You can look back at last week's lab Okay, so this will also sort of make you realize whether the last lab you did it using eye power or you actually did some work. Okay, so let me share the results. Okay, so for the first one, SCGC5, all with this hexadecimal number, more than 50% have said that it is enable power for port D. All right, and for question 2, more than 59% of you have said that this is to make port D bit 6 an input pin. All right, so let's see whether this analysis is correct. All right, okay, so let's look at this. So for this first one over here, okay, can you all see the OneNote that I'm sharing? Yes. Okay, good. Thank you. All right. So if you see this first bit pattern over here, this is hexadecimal, correct? That means each bit here is, or each digit here is 4 bits. So this represents the first 12 bits. That means 0, bit 0, up to bit 11. They are all 0. And bit 12 is a 1. Correct? Bit 12 is a 1. Correct? So that is what this hexadecimal represents in terms of binary. And I'm doing an OR. So when I do an OR with a 1, that bit will be set. So I need to look at this register and look at what is bit 12. Okay, I need to look at what is bit 12. So if I look back here at my okay, my SCGC5 register, okay, you can see that the bit 12 here is referring to port D. Okay, so port D, when I set this to a 1, I'm actually enabling power for port D. Okay, so this is what this is doing. You enable power for port D. All right, so that is the first instruction. The second one instruction here is second 2 lines here is the mask. So here you can see that whatever value you put in, you get shifted left. One gets shifted left by this number of bits. So in this case, when I put in a value of 6 here, that means originally a 1, then I shift left by 6. So 1, 2, 3, 4, 5, 6. Correct? So this is bit 0, this is bit 1, 2, 3, 4, 5, 6. All right. So when I shift left by 6 bits here, but I do a complement here. Correct? So that bit 6 position will become a 0. Okay, become a 0, everything else become a 1. Okay, so when I do an AND with a 0, that bit will be clear, and this is the PDDR. Okay, so if you look at PDDR register, okay, you will see that the 0 means I'm configuring it as a input. All right, so I'm configuring bit 6. Okay, I'm configuring bit 6 of the port D port. So port D bit 6 will be a input. Okay, so that is what this is doing for us. All right, so that is just to give a quick recap on the okay, why the 1 doesn't occupy for it. Okay, so the 1 does occupy 4 bits. It's just that I never put it here. So rightfully, when you do all those bits in front here that is not specified are automatically set as 0. Okay, so the 1 is actually 0001. Right, so this is actually 0001 in terms of binary. Okay, when you convert hex to decimal, each hex digit will convert to a 4-bit binary equivalent. Okay, so here is what I was mentioning about just now, where your main code, okay, some event happens. Okay, some event happens over here. And when the event happens, the CPU does some activities which are sort of, in a sense, transparent, okay, because those are handled by the CPU itself. And then you go to the ISR, all right? And what we are focusing on is how do I capture this event correctly to make sure that the correct registers are configured. I know exactly what event I want to capture. And then when that happens, I sort of develop the ISR code to make sure the correct activities are carried out when the event happens. Okay, this context saving and restoring is automatically done for us in the background by the CPU. Okay, so that is something we can treat as transparent for now. Okay, in terms of interrupts, okay, we say that they are asynchronous, okay, and they can be triggered by a peripheral block, okay, or they can be triggered by external devices. Okay, so if you recall from your EPP, for example, okay, you have your wheel encoder, correct? So your wheel encoder pulses, those are considered an external interrupt, correct? If you have a timer that is running within the processor, that will be an internal peripheral interrupt, okay? And all these are, in a sense, asynchronous in nature, right? And you make sure you have to develop the correct software routines that run in response to these interrupts, okay? So, and this is something that I've mentioned before, it allows embedded systems to be responsive even without an operating system. Okay, so even without an OS in the picture, you can actually achieve some level of real-time response because we have interrupts. Okay, so that is actually a very powerful thing. Okay, so there are two things that we're going to achieve today. We're going to configure the switch, all right, such that when the switch is pressed, we're going to perform some activity, and we're also going to control some LEDs. All right, so this is the sort of the high-level objective, but I'm going to share with you my code later on, which does something similar. Okay, and that will give you some idea on how to prepare for the lab this week. Okay, so let's look at Cortex M0 interrupts. All right, in general, like what we said, hardware interrupts are asynchronous in nature. Okay, which means anytime it can happen. All right, ADC conversion, some data on the serial port, some input line trigger on a rising edge or falling edge. So that is an asynchronous interrupt. You can also have synchronous interrupts, which we can consider as software interrupts, okay, because some fault has happened and so on. Okay, but in our case, we are not dealing with software interrupts per se. We are going to be focusing more on the hardware interrupts. Okay, so the interrupt service routine is basically what you have been writing before, okay, for the Arduino and so on. So we know that that is the code that is executed, okay, specific to the event that triggers the interrupt. Okay, in the ARM controller, we have what we call a NVIC, okay, nested vectored interrupt controller, which is the main sort of gateway between your peripheral subsystems and your core, okay, processor core. So you can see this is like the gateway. Okay, so everything comes into the NVIC and the NVIC triggers the core. All right, so the NVIC is the one that is responsible for managing and prioritizing all the external interrupts that come in. Okay, we will look a bit at how NVIC sort of works, okay, and how it helps us. All right, and in terms of interrupts, okay, or exceptions, there are exceptions starting from 16 all the way to 16 plus n. All right, so this one I will show you later in the data sheet, okay, where you can look at it. All right, in terms of mode, by default, when you first start up the program, you are in what we call a thread mode. All right, but once you are in an exception, we see that the mode will change to handler mode. Okay, so this one later when I'm doing the demonstration, I'll also show you this as well. Okay, in terms of stack pointers, though we have two stack pointers, we do concern, we're not dealing into the low level architecture at this point of time. All right. Okay, so these are some of the interrupt sources that you can see. Now, what I want to do is I want to move out from here and come back to our data sheet. Okay, so if you open up your data sheet, okay, and you go and do a search for the NVIC. Okay, you go and search for table 3.7. This is in page 53. Okay, so I hope all of you have your data sheet open. Okay, so if you look at your data sheet here, you can see that these are the interrupt vector assignments. Okay, and the first address 0 is your initial stack pointer, and your vector 1, which is address 4, is your initial program counter. So this initial program counter is actually the starting point of where your code will execute, all right, once you reboot a system. Okay, and the vectors from 0 to 15 are reserved for the processor. Okay, reserved for the processor. So you can see the source module is the ARM core here. Okay, because these are all internal to the processor, so you cannot touch these interrupt vectors. All right, only from 16 onwards is for the peripheral subsystems. Okay, and you can see that you have different sort of interrupt vectors for different subsystems, for DMA, I2C, SPI, UART, and so on. All right, all the way up to vector 47. Okay, and each of them have their own address. Okay, so inside each of these addresses, what you have is actually the address of the ISR handler. Okay, the address of the ISR handler. That means exactly where is the interrupt service routine located in memory. Okay, so all of this is actually defined here in the table, and this is fixed. Okay, so this is fixed. Okay, with the way this controller has already been designed for us. Okay, so that is from the datasheet. Now let's come back and just have a quick recap on what happens when you detect, for example, an interrupt. Okay, so for port interrupts, you will see that only port A and port D pins are mapped in this current microcontroller configuration. All right. So when an interrupt happens, so assuming that I configure port A or port D for interrupt. Okay, so let's say I configure port D for interrupt. So when an interrupt happens, okay, your NVIC will trigger your processor, okay, and when your processor is ready to accept this interrupt request, it will do in the background the context saving and all, and then what it will do is it will jump to the vector location. So if it's a port D interrupt, it will come to this vector location, and it will take this address and put this address into the program counter, because this is the starting point of where the ISR is located. Okay, so the IRQ handler is basically the ISR. Okay, so that is basically what happens, okay, when an interrupt is triggered, okay, from a very high level perspective. Okay, so at each of these vector locations, what we store is actually the handler address. That means the starting point of the ISR. Okay, so the processor, what it will do is it will jump to the vector location, take this 4-byte address and load it into the PC. So it knows that this is now the starting point of the interrupt service routine. Okay, and then it will start executing the interrupt service routine from there. Okay, so that is basically your how the interrupt vector table actually plays a part, okay, in handling interrupts. Okay, at the same time, your interrupts, your peripheral subsystem interrupts also have a priority level. Okay, and these priority levels are divided into 8 registers called the IPR registers. And inside each of these registers, okay, each of these registers is a 32-bit register. But if you look at the way it is sort of split up, you only use each register to configure for 4 different peripheral blocks. Okay, for 4 different peripheral blocks, and you only use the upper 2 bits. Okay, you only use the upper 2 bits of each of these 8-bit blocks. Okay, so it's here, 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 and here. Okay, so what does that mean? That means if let's say I want to configure the interrupt priority for IRQ 6, okay, then I need to go to IPR register 1, IPR 1, and I need to configure only bits 23 and 22. I don't need to worry about the other bits. I just go to these 2 bits to configure what is the priority level that I want. Okay, so obviously this seems a bit maybe daunting in a sense. So there are some built-in library functions that enable us to do things quite easily in some of these register settings. Okay, and one of this is this thing called the NVIC set priority. Okay, so for this NVIC set priority, what we need to do is basically set the priority based on the IRQ number and the priority. So in terms of priority, we only need to set 0, 1, 2, or 3. Okay, where 0 is the highest priority and 3 is the lowest priority. Okay, now in terms of the actual numbers, it will be 0, 64, 128, and 192. Okay, can anybody tell me why we get 192 here? Yeah, so it's basically the bit 7 and bit 6, correct? Because if you look at it, we are looking at the first 2 bits only. So when these 2 bits are 1 and 1, then this will give you 192. All right, so anyway, we do not need to be worried about these actual numbers. We just need to call this set priority with the appropriate priority value, either 0, 1, 2, or 3. Okay, so this function will automatically do the shifting, okay, and masking to make sure that the correct bits go into the correct location, either 31, 30, 22, 22, or so on. Okay, so we do not need to specifically move the bits to those locations. We just call this, make sure we provide the correct number and the correct priority, and the shifting and masking of all the bits is done automatically for us, okay, in the function. Okay, NVIC is basically a hardware block. Okay, the hardware block that is part of the processor. Okay, so when interrupt is triggered, okay, all these peripheral interrupt blocks are actually send some signals to the NVIC block, which will then prioritize all these multiple requests and decide who should go over to the processor to trigger the interrupt. Okay, so the NVIC is a hardware block that is part of the processor core. Okay. Okay, so in terms of enabling and disabling interrupts, okay, there are 2 functions that you can easily use. One is enable IRQ. Okay, one is enable IRQ, the other is disable IRQ. Okay, based on the IRQ number. Okay, and there are also another 2 other functions here: set pending IRQ and clear pending IRQ. Okay, we will see in a while why we need to that these are there, but we don't actually have to use them. All right, even without using them, they will still work. Okay, but they are there because of some legacy reasons. Okay, so in the past, due to certain behaviors in earlier processor cores, they had these functions, but they've carried on these functions even though they don't necessarily have to be used with the current generation of processors. All right, in terms of overall global interrupt. Okay, so if you remember your Arduino, also there's a global interrupt enable and disable pin. So almost all processors have this. So in our case, there's a global mask register called the prime mask register. Okay, and bit 0 basically configures this global enable and disable. Okay, so if I set it to 1, it prevents exceptions. Clear to 0 is to allow exceptions. Okay, and in order to configure this flag, you also need to use these built-in functions. All right, so there are certain built-in functions that you have to use to configure certain registers. All right, because directly there is no way to access them. You have to use these inbuilt functions. Okay, in terms of priority, okay, like what we saw just now, there are 4 different values. Okay, 0, 1, 2, and 3 here. Okay, so this is 0, 1, 2, and 3. Okay, so this is of course the representation in the 8-bit. Okay, in terms of some exceptions, they are fixed. Okay, so if you look back at the ones at the ARM core level, okay, the first 16, those are fixed. Okay, that means you can't touch them. The rest of them are adjustable. Okay, so if you look at all the peripheral subsystems, your SPI, UART, I2C, and so on, all of them you can adjust the priority depending on how you are designing the system. Okay, so if there are simultaneous exception requests, that means multiple interrupts coming at the same time, correct? So you have your block here and you have multiple interrupts coming in. The lowest exception number is service first, correct? Because lowest exception number means highest priority. Okay, so this one is quite standard across most processors. Okay, but new exception requested while a handler is executing. That means I'm in the middle of an interrupt service routine, right? And then what should I do? So if the new priority is higher than current priority, the new exception handler preempts the current exception handler. So if I'm in my main code, okay, an interrupt comes in, I jump to ISR1. Okay, and in the middle of ISR1, if ISR2, which is higher priority comes in, I will preempt ISR1, jump to ISR2, okay, finish ISR2, then come back, finish ISR1, then go back. Okay, so that is basically preempting the current exception handler. Okay, so if the new priority is lower than or equal to current priority, then the current ISR will be held in the pending state. Okay, that means I will keep it, I will register it. Okay, that means I know that the interrupt has been triggered by the peripheral block. Okay, but I will only service it after that, after I finish my current interrupt service routine. Okay, so that is the behavior of our processor call here. Okay, so now let's look at this example using port module and external interrupts. All right. So like I said, we are going to focus on the switch, okay, and ISR, as well as the main code to control the LED blinking. Okay, so this, so if you look through the data sheet, you will see that we have a lot of ports, port A to port E, all right? And then if you look at the interrupt vector table, there is only port A and port D for interrupts, all right? And this is because of the current configuration of this microcontroller, all right? So even though the processor core itself is actually able to handle multiple interrupts from all the ports, okay, but because of pin multiplexing and all these limitations, there are only certain ports or certain pins that are available for some of these functions. So based on the current design of this chip, okay, on the board, only ports A and D support interrupts. Okay, so we need to limit our interrupt features to this. Okay, so in terms of our setup, okay, that we're going to be doing for the lab, okay, we're going to be using port D pin 6 over here. Okay, port D pin 6 to connect as a switch input. Now, when I look at this configuration here, okay, so this is a push button switch. Okay, one end is ground and the other end is connected to port D. All right, so now if I were to just give you this circuit like this, okay, and there's no other information, when I close this switch or when I open this switch, what is the logic level at port D6? Okay, if it is open, what is the logic? If it is closed, what is the logic? Or what is the voltage? Okay, so there are some answers. Okay. Okay, so I think close, yeah, it's quite easy to see that if I close it, okay, if I close it, I will create a direct short circuit to ground, so you can say it's 0. But when it is open, okay, when it's open, it is undefined, it's floating. Okay, because if it is open, I'm reading from this point over here. But this point over here is not connected to anything, correct? It's not connected to VCC, it's not connected to ground, correct? So it is open, it's floating. So this is definitely wrong, correct? There's something wrong with this design, okay? But it is it can be used in our context, okay, because of something that we have also seen before, which we're also going to see here, something internal to the GPIO pin that we can enable. Okay, and anybody want to guess what is that? Yes, correct. It's a pull-up resistor. Okay, so if you have pull up or pull down internally, then you can use this configuration. Okay, what do you mean by internal pull up? That means if I were to look at the GPIO pin, okay, so even though I connect it here, internally, that means this is something you can't see, it's internal to the controller, there could be a pull up to VCC. All right, so this is something that is internal to the pin. All right, and most microcontrollers that support this will also have some configuration to enable or disable this. Okay, I'm not sure if you remember, but in your EPP2 you also use this. All right, when you are connecting your encoder interrupts to the GPIO pin, all right, you also had some pull-ups to be enabled. All right, so we did see this in the Arduino Uno, and this controller also has this feature. Okay, so we'll be seeing how to configure all of these for our controller, okay, and use it correctly. All right, so let's look at a bit about the program first. So definitely when we write the program, the first thing is we want to initialize the system by configuring the switch, configuring the LEDs. Okay, so these initializing switch and LEDs are basically things that we have already, you sort of know from last lab, okay, because we are just dealing with the input and output. Okay, so what is new, what is different is this initializing the interrupt. Okay, how to make sure that the interrupt is configured correctly. Okay, once the interrupt is configured correctly, then rightfully whenever I press the switch, I should be able to jump to the ISR, and in the ISR I either control the LED or change some count value or something like that. All right, and of course in some cases you also have variables that are shared. Okay, so you need to decide, all right, what are these shared variables. Okay, you need to see whether they need to be declared as volatile. All right, and you also need to check whether the access to this is atomic. Okay, so volatile and atomic we will look back again later towards the end of the slides over here. Okay, so these are some of the main things here. Okay, so I will not go into these details here. Later when we look at the code, then we will examine this in more detail. All right, in terms of configuring the interrupt, we need to make sure we set up the peripheral module to generate interrupts. Okay, in this case we will use the port module. We need to set up the NVIC. Okay, so when we say set up the NVIC, we are basically configuring the NVIC in terms of which are the priority levels, okay, that we're going to set for the interrupts and which interrupts are enabled. Okay, so we need to enable interrupts, we need to set the appropriate priority levels, okay, and we also need to make sure that the global interrupt is also enabled. Okay, so these are some of the things we need to take into account. Okay, so in terms of the port module, okay, like I said, the NVIC is internal to the processor core. So all the port pins that can generate interrupts will go through a port module. Okay, and this port module will register the interrupts coming in from these GPIO pins. All right, so if you remember from last lab, we have this register called the PCR, port control register, pin control register. This pin control register is actually controlling a lot of things. All right, so one of the things we saw was multiplexing. All right, so you can configure each pin and select its multiplexing option. And today we're going to see how we can use the same register to configure some of the interrupt capabilities as well as the pull up or pull down capabilities of those particular pins. Another register that we're also going to look at is this thing called the ISFR register, interrupt status flag register, where if an interrupt has been detected, okay, you will set that particular bit to 1. So that will actually help to send the appropriate signal over to the NVIC, telling the NVIC that this particular port is actually has registered an interrupt and is requesting attention. Okay, so that is basically how the peripheral blocks are actually going to send the interrupt request over to the processor. So the NVIC is the middleman. All right, it takes in these requests from the peripheral blocks, all right, and then looks at all the requests, the priorities, and decides how to manage them, okay, based on the requests from the peripheral blocks. Okay, so let's look at the pin control register first. Okay, so let's go to our data sheet. Okay, I always like to go back to our data sheet, all right, so that you have the idea of how to extract information from the data sheet directly. Okay, so can everybody see the data sheet I'm sharing? Okay, can, thank you. Okay, so for this pin control register, as we saw, each port has 32 bits and each bit has one 32-bit PCR register associated with it. Okay, each bit has one 32-bit register, PCR register associated with it, because we can configure each bit individually. That means each pin can be configured individually. All right, what we saw last time was this pin 8, 9, and 10. Okay, and pin 8, 9, and 10, as we saw, was to configure the multiplexing option. Okay, so 001 was the alternative one GPIO, okay, for most of the pins. All right, so now what we're going to be looking at is your two things. One is IRQC and the pull up. Now IRQC over here, if you look at the configuration here, it is to detect for the interrupt configuration. Okay, so for interrupt configuration, if I want, for example, I want to generate an interrupt, okay, on logic level, okay, logic 1 or logic 0, then I use these bits. If I want edge rising or falling or either, then I use any of these bits. Okay, so the IRQC bits is to configure that particular bit, whether I want it to generate an interrupt, okay, when I detect any of these events. Okay, DMA request, we are not looking at it, but it's another feature you can use. That means I use an external device that wants to initiate a DMA can actually assert a GPIO pin to request for a DMA transfer. Okay, DMA, we will look at it in a later chapter. Okay, so we will not go into that now. All right, so you'll focus on the interrupt on either edge or logic level over here. Okay, so that is your IRQC. Okay, so that those bits you can configure. The other one is your PS and PE. Okay, so if you look at PS and PE, it's basically your pull up and pull select. Okay, so in this case, you can, if you want to do the pull, you can first decide whether you want pull up or pull down. So if you see down the pull select, if it is 0, it is a pull down. Pull down means you have a resistor pulling that pin down to ground. If it's a pull up means you have a resistor pulling it internally up to VCC. All right, so you can decide pull up or pull down. Then after you decide this configuration, at the same time, you can also enable or disable. Okay, so this will sort of internally configure the hardware configuration, okay, of your device that is connected to that particular pin. So in our case, since we have a switch, all right, and the switch, the other side is connected to ground, the side is connected to the port pin, we can do an internal pull up, all right, which is what we are going to be doing. Okay, all the pins have both pull up and pull down. Yes, all the GPIO pins have this capability. All right, but if you want to check, you always go through each and every the register of that particular pin. Okay, but generally all the pins have this. Okay. Okay, so those are two things for your PCR register. Okay, so now what I'm going to do is I'm going to share with you the code. I'm going to go through the code structure, okay, on how to set up LEDs and configure the switch and everything to make sure we get it right, okay. But I think before that, maybe we can go for a short break now. Okay, now it's 9:50. Okay, so let's have a short break. Come back at 10. I give you a 10 minutes break. At 10 o'clock, we come back and we'll be going through the code in detail to examine how to do everything step by step in terms of setting up the LEDs, switches, and configuring the interrupts. Okay, and then we will see how to put everything together. Okay, so that you know what to do for the lab. Okay, so I will stop the sharing now. Okay, I'll see you back here at 10 o'clock. Okay, so let's get back. So for this week's lab manual, which I already released, you need to use one of the ports. Okay, so if you haven't soldered the header pins yet, all right, no need to rush. Okay, as long as you solder the one on the left over here. Okay, so if you see the board here and the picture here, basically the two connectors at the bottom. So the only connector you need for this week is the one on the left hand side over here. Okay, so if you haven't soldered the rest, at least make sure this left hand side connectors, okay, that means with the board facing you and the USB ports below, okay, the connector on the bottom left. Okay, so at least make sure that part is done. Okay, the rest you can still do slowly. Okay, but for this week's lab, you need this to be done. Okay, so as you can see over here, we are connecting it to ground and port D6. So ground is on the left hand side, 1, 2, 3, 4. Okay, so if I zoom in here a bit, okay, so the ground will be, so I'm trying to show you how to connect. So it's 1, 2, 3, 4. So this will be a ground. Okay, the pin 4 from the left up. Okay, and the pin port D bit 6 will be here. Okay, so this will basically be your GPIO push button switch connect. So a push button switch, okay, will be connected this way. Okay, so that is basically the hardware configuration that you need to do. Okay, so make sure the left hand side connectors are there and you plug in your switch in this manner. Okay, so the switch that is given to you, you just need to make sure you solder two wires. Do not use the prototyping wires, those ribbon cable wires. Okay, use the normal wires in the lab. Okay, and then you just solder at both the joints. Okay, and you should be able to see. All right. Now, once you connect up the hardware, okay, so let's look at the software side. Okay. Okay, so on the software side, okay, for initialization, okay. Okay, so there's a the sharing here by Neil. Don't heat up the contacts too much because it will melt the plastics. Yeah, so try to keep. I think you should never keep the soldering iron on the contact for too long. Okay, so make sure you prepare, and the moment you put the soldering iron on the pad, okay, or on the contact, it heats up very fast. It heats up very fast. So the moment your soldering iron touches the pad or the connector, immediately put the soldering lead and it will melt. Okay, if you keep it on for too long, okay, it will most likely burn the contact or damage it. Okay. Okay, so for the software connection, software part here, you need to enable port B and port D. Okay, so that's the first thing you need to do. So your SCGC5 is your register that does this for us. Okay, so this part we know. Then your PCR marks. Okay, all the 3 GPIO pins which are going to be used. Okay, for the port. Okay, we need to configure them. And of course the LED as well. Okay, so this is for the LED configuration over here. Now, So once your LED configuration is done, okay, so if you look back at my main code here, there is also another very important thing, which is the switch connection. Okay, so for the switch connection, all right, let's look at it quite carefully. So there's a few things here. So the first thing here is you enable the port. Okay, so this actually maybe it's not necessary in this case because you already enabled it over here. Okay, so because you already enabled it over here, port DMAS. Okay, but I just added it here in this case so that I sort of uh, separate out switch and GPIO. So in some cases, if I just using switch without the LED, the switch will still work. All right, so I don't need to depend on the GPIO or the LED configuration to switch on the power for the switch. Okay, so now the important thing is this part over here, port D PCR. So this PCR is your pin control register. So you need to specify which bit you're talking about. Like I said, there are 32 such registers for each of the port pins. Okay, so in this case, switch position is the definition that I've already hex defined based on the switch that I'm using. Okay, so there are a few configurations here. So the first one here is port PCR mux. Okay, is enable clock of that port equivalent to enable that port? Yeah, basically clock enable or clock gating is to make sure the power is supplied to the port. All right, if you do not supply power to the port is not going to work. Okay, I mean in general I'm saying port, but it basically for all peripheral blocks. Okay, you need to make sure that the clock is enabled, then the peripheral block will be able to function. Okay, if not, it's not going to function. Okay, so the first thing over here is port PCR mux 1. Okay, so when you look at port PCR mux, okay, if you go to the definition, okay, it is basically shifting it, okay, to and doing a and with the mux and mux mask is this bits here. So this one is something that we did, we saw last week. Okay, so the mux is basically to configure that I want to use it as a GPIO pin. So if we come back here, so let me go back to our PCR over here. Okay, so the mux over here is basically configuring these bits over here, bits 8, 9, and 10. Okay, so if I put a value of 1, then I'm using it as a GPIO pin over here. Okay, so that is your first part of the configuration here. Now, the second, these two lines is basically to enable the pull up enable and pull select. Okay, so this and this PS mask and PE mask is to say that I want to enable the pull up and I'm going to enable the pull up configuration. Okay, do we need to enable IRQ? So by default, it is already enabled. Okay, so you do not need to do that in the code. Okay, by default, it is already enabled. Okay, to allow exceptions to occur. Okay, now the next thing is the switch position here. You set it to input. So that is what we're doing here. So the port direction register, we do a complement to make sure that that particular bit is set to input. Okay, then these three things. Okay, so these three things are basically to make sure that you set the priority. Now, so this is important. How do I know the name? Okay, in my lecture slide just now, I say you must use the port, the ISR name or IRQ name. So how do we know the name? So how do I know I must use port D underscore IRQN? So where is this defined? Okay, so for each interrupt, you must use the correct name when you are calling the NVIC library functions. Okay, and these names are actually defined inside your header file, your MKL25Z4H. If you go all the way to the top, this is where your IRQ numbers are defined here. So this is important. You must use the correct name that matches the interrupt. Okay, so if you scroll down, the port interrupts are here. Port A IRQN and port D IRQN. Okay, so you must make sure you use the correct name depending on the interrupt you are configuring it for. So in this case, I'm using port D, so I must use port D underscore IRQ N, a small n, for my configuration using when I use the NVIC library calls here. So the first thing is I set the priority. Okay, so in my case, I just set priority 2. If you set 0, 1, 2, or 3, doesn't matter in this case because it's only a single interrupt. Okay, so this number doesn't matter in this case. Next is clear pending IRQ. Okay, so this clear pending IRQ is to do what? Okay, if the moment there is a interrupt triggered, okay, the NVIC will capture it. Okay, now this clear pending IRQ is to make sure that in the event that because in some cases, okay, you may have a situation where you enable the interrupt, in the maybe one part of the during some time of the application, and maybe halfway through you want to disable it, and then you want to re-enable it again. Okay, so in that situation, if there's any leftover IRQ that was still pending, okay, before it was disabled, you want to clear it so that you do not have to quickly service it the moment you enable it again. Okay, so that is why you have a clear pending IRQ. So this will help to clear any IRQ that was pending prior to you enabling it again. Okay, then the last part is to enable IRQ. So when you enable IRQ, it will now start to be able to capture interrupts. Okay, it will capture interrupts based on the configuration. Okay, so what is the configuration? So we come back here. This is the important part here. Port PCR IRQC 0x0A. So 0x0A means I look at the IRQC configuration. So if I come back here, okay, IRQC A is 1010. That means interrupt on falling edge. Okay, that means now right now I'm configuring this device to interrupt on falling edge. Okay, so that is the configuration that I have now set up for this particular pin connected to port D pin 6. Okay, connected to port D pin 6. Okay, so that is basically the entire setup that you need to do for the switch part. Okay, so that is your init switch, init GPIO. So these are two main functions first, and then you have all right. So once that is done, okay, you are already able to accept interrupts. So now the next thing is when an interrupt happens, okay, when an interrupt is triggered, okay, what is going to happen now? Okay, what's going to happen? So let's look at that now. Okay, so there's some questions here first. Could there be multiple ISR setup at port D? Yes. Like I said, when you take each of the port A or port D, the PCR registers for each individual bit, correct? So you can set up them separately. Okay. But for the handler, okay, for the handler, there's only one handler. Okay, there's only one handler. That means inside the handler, you then need to decide or do some checking to see which bit was or which bit triggered. Okay, so there is a register for that. We will look at that in a while. Okay, to set up priority separately, okay, basically you can set up priority, okay, based, you cannot set up priority separately for individual bits, okay, because the priority is based on the port. Okay, so for entire port D, you have a particular priority. For entire port A, there's a priority. Okay, so you cannot individually set the priority for the individual pins. Okay, IRQC sets config. Okay, IRQC PCR register is for individual bit. Okay, that means you can say, okay, so for example, I can say that port D bit 6 configure interrupt for falling edge. Port D bit 7 configure interrupt for rising edge. Okay, so each individual bit I can configure interrupts differently. But eventually, when any of them trigger, it will still jump to the same IRQ handler. Okay, then inside the IRQ handler, I can check and see which bit trigger the interrupt, and then I take the appropriate action. Okay, so the IRQ handler is universal for that particular peripheral block. Okay, so let's look at the IRQ handler first. Now inside this IRQ handler, in my case, all right, okay, you can see that it's very simple because I am having only one interrupt. Okay, but if I want to know which particular bit triggered the interrupt, there is this flag called the interrupt status flag register, ISFR. Okay, so let's look at that over here. Okay, so if you look at this register called ISFR, interrupt status flag register. So if you look at the description, okay, this pin interrupt is very, okay, if it is a 1, the configured interrupt is detected. Okay, that means in the situation where I have multiple bits in the same port configured for interrupt, I can check which of the bits triggered or which of the pins triggered the interrupt by looking at this interrupt status flag. Okay, so it is a read-only pin. Okay, so I can read this register and I can know whether that particular bit or interrupt has been triggered by the peripheral system. Okay, so that is how I can differentiate. Okay, but in my case, okay, since okay, so how is this different? So this is basically the ISR. Okay, the IRQ handler, which we call it here, is basically the ISR. All right, so this port D IRQ handler will make sure or this is a code that will actually execute when I detect an interrupt on port D. All right, so it is a universal handler regardless of any of the bits or any of the pin configurations for port D. All right, so once I detect this interrupt, okay, this event, I'll come in here. Okay, so this part here, okay, this variable incrementing also, because this is part of what you want to do. Okay, but what is important is this: you need to make sure you clear the INT flag. Okay, so this flag, okay, in the port D ISFR register, that particular flag corresponding to the bit. So in our case, we are dealing with port D bit 6, right? Because our switch is connected to port D bit 6. So later on, you will see that when I come to this particular line, the port D ISFR register bit 6 would be set. Okay, because that means it has detected interrupt on that particular pin. Okay, and I need to clear this bit. Okay, I need to clear it by ORing it with a 1. Okay, so if you look back here, the flag remains set until a logic 1 is returned to the flag. Okay, that means to clear it, I must write a 1 to it, then I clear the flag. Okay, so when I clear the flag, then only it will stop sending interrupt requests to the NBIC. Okay, if not, the port D port module will continue to send interrupt requests to the NBIC. Okay, so this is important. This is basically what we must do to make sure that we clear the interrupt. That means we say we already serviced the interrupt. Okay, if not, what will happen is the port module will continue to send your interrupt request to the NBIC block. Okay, because it thinks that the system is still being triggered. All right. Now this clear pending IRQ. So this is from the NBIC side. The NBIC side, this is actually not necessary. Okay, but the reason why I put it there is because, like I said, you may refer to some online resources, some books, and you see this line there, and you say, "Hey, how come I don't have this?" Okay, this was there for legacy reasons. You remove this, it will still work. Okay, so later I'll show it to you as well. Okay, but this is to clear the pending IRQ. But from the NVIC side, the moment it handles a particular IRQ, that means the moment it jumps to the interrupt handler, it will automatically clear its request within its NVIC block. Okay, so you don't actually have to do this, it's done automatically. Okay, but having this there also does not change anything. All right, but what is important is you must clear the ISFR flag in the appropriate register. Okay, so in this code, basically what I'm doing is inside the IRQ handler, I am incrementing some variable and I'm also toggling this LED control. Okay, so this particular bit LED control will keep changing. Okay, and then if this LED control is set, I will toggle the LED. If not, I will off the LEDs. Okay, so this is my code, which is not exactly what you're supposed to do. You're supposed to run through RGB, and so on. Okay, but I'm just going to demonstrate this code. Okay, and then in the lab you can extend and implement your own functions. Okay, so let me compile run this code, and then we will step through some of the important parts so I can show you what is happening. Okay, so the first clear pending IRQ is not necessary. Okay, so the first clear pending IRQ over here. Okay, so this is not necessary. Even without this, it will still work. Okay, so this is at the NVIC block side. This is at the port block. Okay, the second one over here. Yeah, so this is on the NVIC side, and this is not necessary, but this one on the port side is necessary to make sure that we stop the port from sending interrupt requests to the NVIC. Okay, so let me run this and show you what happens first. Okay, so as you can see, by default, the LED is blinking on and off. Okay, so that is the default code here. Okay, and what I hope you can see here is the LED control value here. So rightfully what will happen is when I press the switch, when I press the switch, it should trigger the ISR and jump to the ISR. Okay, so maybe what I'll do is I'll put a breakpoint here. Okay, and let's see what happens. So when I put a breakpoint there and I press the switch, it comes here. So let me explore a few things here and show you. So the first thing here is on the left hand side, you can see that the mode of operation here is now handler mode. Okay, which indicates that we are currently in an interrupt. Okay, so that's why we're in a handler mode. Now another interesting thing you see here is if you look at the PSR. Okay, yeah, so finally it's here. Okay, so the magnifier is here. So here you can see that in the mode of operation, I'm in the handler mode. Okay. Now another thing I want to show you is the PSR value here. So if you look at the PSR value, ISR is 47. Okay, so what is ISR 47? So if you, okay, the 47 refers to the interrupt vector over here. Okay, and that corresponds to port D module. So by looking at that PSR register, we can say that we know that we are currently servicing the port D interrupt request. Okay, so that is the handler mode and the interrupt request that is registered in the processor at the time. Okay, so that are two things. Now I'm inside this IRQ handler. All right. Now another thing I want to show you here is this value over here. So if I go and add this, so you can see that this value here, if I add this to watch, okay, so you can also see the value here is hex 40. So this corresponds to bit 6 being set. Okay, hex 40 corresponds to bit 6 being set, and that bit 6 corresponds to the switch position. Correct? We have connected the switch to port D bit 6. All right. So you can see that basically what we are doing here is we know that this register also signifies or tells us that in port D bit 6 is the one, or the peripheral connected to bit 6 or port pin 6 is the one that has initiated or triggered the interrupt. Okay, now let me put one more breakpoint here, and if I run it, okay, you see that now I clear it. Okay, so now the value is clear, right? And once the value is clear, that means I've already serviced the interrupt, so I will no longer send interrupt request to the NVIC. Okay, so let me go ahead and run. Okay, so now that I've pressed the switch, I have toggled the value of LED control to 0. Okay, so in my code over here, I will be switching off the RGB. So that is why, okay, where's my RGB? Okay, so that's why my RGB is now off. Okay, so that is what is happening in my code over here. So if I press it again, okay, so you will see that it's not so responsive. Okay, and another thing you'll notice is I also increment a count, integer count. So rightfully, every time I press it one time, it should increment once. Okay, but you look at the value here, count. Okay, you will see that the value jumps a lot. Okay, the value jumps a lot. Okay, from 65, it suddenly jumps to 100 and so on. Okay, so it keeps jumping a lot, and at the same time, the LED control also doesn't toggle as expected. Okay, and the reason I think all of you should know, correct? Yes, debouncing, correct. Okay, so it's basically the mechanical debouncing issue. Okay, the mechanical debouncing issue that causes multiple triggers, okay, to be captured. All right, so of course, how to handle debouncing, you have hardware solutions, you have software solutions, and so on. Okay, so I'm not going into that. All right, but the whole idea is, as long as you understand how to set up your interrupt and configure it, all right, and inside your interrupt routine, you make sure you go in the correct sequence, right, to fulfill the requirement. So in your lab, you're supposed to do something similar, except that you're supposed to make the LEDs go from one LED or go in sequence. Correct? Every time I press the switch, it goes from R to G to B and so on. Okay. So one thing you can do, okay, for those of you who are coming to the DSA lab this Friday or anytime next week, all right, you can actually hook up the oscilloscope. Correct? That means you can connect the switch to the breadboard, and then from the breadboard connecting it to the port D pin 6. So that will give you, or you can directly clip it to the switch as well, and observe the debouncing. Okay, so when you observe the debouncing, you have a rough idea on how long is this debouncing period. Okay, and of course, one of the easy ways is you just buffer or put a delay until that time lapse, so that you can then get past the debouncing and you don't get any false triggers. Okay, so that is of course a very simplistic solution to going around the debouncing issue. Okay, so that is basically what I want to show you, and that is what you need to be doing and preparing for the lab. Okay. I'm sorry, today my laptop is just super slow, so everything is very slow. I don't know why. Okay, so let me carry on with the rest of the slides first. Okay, so that, okay, finish up. So this is what we did just now. We examined the code, okay, in terms of how to configure the LEDs, the switch. So as you can see, there are a few different steps involved. Okay, the clock gating, mark setting, direction, pull up, enable, setting up the interrupt priority, and of course enabling the interrupt. Okay, so these are things that you need to make sure you do it correctly. Okay, when you're doing the lab. Okay, and then you write the interrupt service routine. Okay, make sure you use the correct names as well. Okay. Next is so all these things we have sort of gone through. Okay, the sequence and everything. And of course, one of the things I think we all know is you don't have any arguments or return values, correct? Because you do not know when the interrupt will happen. Okay. So of course you can have shared variables between interrupts and main routines, which we will look at that in a while. Okay, so this is an example of a interrupt service routine. So in this case, you can see that if I want to be really sure, that the interrupt was triggered by this particular port B bit 6, then I can do this. Okay, so what does this do? This actually helps me to check that port D bit 6 is the one that actually triggered the interrupt. Correct? Like I said, all of the bits on all of the pins on port D can all trigger interrupt, and all of them will come to the same hierarchy handler. Okay, so inside the hierarchy handler, you can do this kind of checks to take different actions depending on which pin trigger the interrupt. Okay, and this one is, of course, you do a blanket clear, and that means effectively you clear all the interrupts at the same time. Again, this is just a simple hack. If you want to be very specific, then you also do something like the mask, correct? So you can clear the status flag inside this check over here. Okay, so inside this check. Okay, so if I check that this particular bit has a pin has triggered the interrupt, then after I take the appropriate action, I can clear that particular bit in the ISFR flag. Okay, so that is up to you, right? So in this case, since I only know that that particular bit is tied to interrupt, I can just clear all the bits, doesn't matter. Okay, so these are things you do. Okay, and of course things like this. Okay, so if things do not go as well, or if you think you want to examine in more detail, you can set breakpoints in the ISR. Okay, and then you can check. All right, check for your data, check what are the variables, are they changing correctly. Okay, and of course, if you don't see anything happening, you must first set a breakpoint at the start of the ISR to make sure that you actually have jumped to the ISR when the push button was pressed. Okay, so if things don't work, okay, you need to check on both the hardware side and software side. Check on your side whether the switch is actually functional. When I press, does it actually form a closed loop? Okay. Next, if the hardware is correct, then you look at the software side. Okay, so you look at, did I configure the GPIO correctly? Did I configure the interrupts correctly? Did I do the proper clock gating and so on? Okay, so for the ISFR register, it is one of those registers where if it is triggered, you set to 1, but to clear it, I must also write a 1. Okay, so in your microcontroller, there are registers that behave like that, correct? You, to clear that bit, you need to write a 1 to it. Okay, so this is basically information that you must get from the data sheet, right? To know exactly how to configure it. Okay, so let's look at some timing analysis first. So this is, for example, a situation where you are monitoring the switch, all right? And you look at the time in the ISR versus time in the main, okay? So obviously, if you look at it from a very macro perspective, it looks like as if you're always running the main program, okay? Even though the ISR is triggered over here, okay? But if you zoom in, then you see that, okay, at some point of time, okay, you actually have a break from the main, okay, and you jump to the ISR over here. Okay, so this is indicating that there is, from the broader view, it seems like as if the main program is always running, but when the interrupt is triggered, you actually sort of suspend the main program to jump to the ISR, okay, and then you can come back after that. Okay, next is another thing that we need to talk about, the latency, okay, where it is the time delay. All right, and what is this time delay constitute of? You first need to finish the current instruction you're executing. Okay, so you need to finish the current instruction. Next, you need to push various registers onto the stack. Okay, and then you need to fetch the vector. So this pushing onto the stack, fetching the vector, all these are in a sense transparent currently because they are all handled by the processor. Correct? And then we also need to then jump to the vector. All right. So all of this plays a part. Of course, there can be other factors. For example, in terms of memory, okay, if you are using external memory for the stack and so on, then all of this also may add up, okay, to the time that it takes for me to be able to actually start executing my interrupt service routine. Okay. So there can only be so many interrupts that we can handle per second, right? So this is just some idea on how we can actually calculate the rate. So if I have a CPU that is running at a particular frequency, and I can say that my each interrupt, okay, takes a certain number of cycles plus some overhead, then the maximum interrupt rate can be CF CPU divided by the number of cycles that the ISR takes plus the number of cycles, the overhead that are involved. Okay, but of course this is also not truly accurate, because in this case I may be only looking at only one interrupt. Okay, so when you have other interrupts, then this also isn't truly valid, correct? And then your utilization is the fraction of the processor time consumed by interrupt processing, where every time an interrupt comes in, you need to abandon what you're doing and go and service the interrupt. All right, so you need to look at the fraction of this interrupts, okay, the frequency of these interrupts, all right, and then look at how you can calculate this. All right, but again, this is just some maybe high level view, which is not truly accurate, right? Because in a system there will be many interrupts, okay, there can be many dynamics in place. All right, so in the tutorial next week, you will actually examine some idea of how to look at these numbers, okay, but this is just to give you some idea only. Okay, so program design with interrupts, right? These are again things that we need to think about. All right, how much work to do in ISR? Okay, should ISR re-enable interrupts? Okay, that means if I'm already in ISR, should I re-enable interrupt for the same ISR again? Okay, if it is allowed. Okay, and how do I communicate between ISR and other threads of ISR and the main program? So these are important things. All right. Of course, you want to make sure your ISR is as fast as possible. Okay. If you have multiple ISR short deadlines, you want to perform critical work in the ISR. All right, and then you want to buffer partial results for later processing. All right, so we always want to make sure ISR is short and simple. Okay, now an important thing is sharing data between ISR and other threads. So this leads to two important things. One is volatile data, which we have seen for EPP students, you've seen this before. So when you say data is volatile, that means it occupies some space that could be updated, okay, even without executing the current code. Okay, that means it could be through an interrupt, or it could be through a hardware interface. Okay. Okay, non-atomic shared data. Okay, when you have non-atomic shared data, that means you have a situation where, for example, I have a buffer. Okay, let's say I have a 100-byte array. Okay, and your main program is supposed to okay, sorry, my computer just froze again. Okay, so your main program is supposed to read from it, and your ISR is supposed to write to it. Okay, so if this 100 bytes represent this full 100 bytes represent one instance of data, okay, that means rightfully when the main reads the full 100 byte, it should be able to read it without interruption. And when the ISR writes to it, it should be able to write it without interruption. So imagine that the main program read, and then halfway through, at some point of time, you get interrupted. And then by the time you come back, the ISR updated already. So that is the issue, right? Because the main program has read halfway through of some old data, and is now combining it with a second half of a new data. All right, so these are all issues that we need to handle. All right, when you have shared data between a main program and a ISR. Right, so this leads to these issues, or what we call a race condition. Okay, where the timing, relative timing of read and write operations are critical. Okay, so we need to make sure we handle this, and this leads us to a critical section of the code. So what is the critical section of the code? That means, like what I mentioned just now, if I have this 100-byte array, then I can say that as long as I'm trying to access this 100-byte, okay, as long as I'm trying to access this 100-byte, this is considered a critical section of the code that tries to access this 100 bytes of data. Okay, that means once I start to read from it, okay, nobody else should get access to this. Okay, so if the main has started reading from this, and if halfway the ISR comes in and the ISR wants to access this same data, you should not be allowed to do it. Okay, so those are things that we need to handle. Okay, so you can handle them. Of course, when you go to OS, you will see that there are a lot of very nice sort of features in the OS itself that help us to achieve all this. All right, but without an OS, you can also achieve this. Okay, but we need to think of how to do it. Okay, so there are different ways of looking at it. Okay, which we will discuss in the tutorial. Okay, so that is all I have for today in terms of the interrupt, okay, and the exceptions handling. All right, like I said, we will cover and discuss more of this in the tutorial next week. Okay, we will discuss more on these interrupt concepts. Now, so a few things before you all log off. For this Friday, like I mentioned, you need to make sure you have at least the left hand side bottom left part of your header pin soldered, all right, and your push button switch is also soldered. All right, so if that is done, then no problem. Okay, but unfortunately this week, Monday to Thursday, the lab is fully occupied. Okay, so only Friday slot is available to use the lab. Okay, so if this Friday you are not able to come to the lab or you're not coming to school, it's fine. Okay, you can still take the lab session online. Okay, so if your hardware is not set up, one alternative is you can come next week. So next week, Monday to Thursday. Okay, next week fully Monday to Thursday, the lab is free. Okay, because EPP is fully online next week. Okay, so next week, Monday to Thursday, anytime you can come in and you can use the lab to do your soldering, or you want to build up your robot or what, is up to you. Okay, so that is what I wanted to say. Okay, another thing I want to clarify is on the lab demonstration and the grouping. So for the weekly labs that I sent to you all to do, there is no particular grouping involved. Okay, you are free to work with whoever you want. Okay, so it doesn't have to be from your same lab slot. Okay, you can work with anybody you like, your project teammates, your friends, whoever. Okay, so there is no particular grouping for the weekly labs. All right, but what the TAs will do is they will have individual demonstrations scheduled for you all. All right, so whoever you work with doesn't matter, but you need to present individually to the TAs, and then they will ask some questions, okay, or maybe from your code or from your hardware. And as long as you answer them, then you're cleared. All right, so you can work on the individual labs, on the weekly labs individually or with anybody you like. All right, but demonstration is done individually. All right, so these are the two things I wanted to clarify, because these are the questions I've been getting from most of you all. Okay, so zoning still is in place. That means as long as you're not part of the zone in engineering, that means zone A, if you're not part of this zone, you are not allowed to come to DSA lab. All right, the alternative for those of you who are in zone C, I mean SOC, you can go to the makers lab. Okay, the makers lab also has a few soldering sessions and oscilloscopes all set up there. All right, so that is the alternative place for those who are not in our zone. Okay, yeah, oh yeah, I mentioned about the delay function to use that you all can use. Okay, I forgot about that. Okay, I'll send it to you all now. Okay, in the lab folder now. Okay, so I'll send you all a simple delay function that you all can use so that for the LED blinking and all, you can use that. Okay, I'll do it now. Okay, so I see some discussion about the why we need, how it's configured for the ISFR register one. Okay, so all these are part of the, not exactly C syntax. This is your hardware description language. Okay, so in terms of uh, when you are, I think some of you are learning hardware description language modules. All right, so in those modules, you are writing code to configure hardware. So you can configure hardware that behaves this way. All right, where I write a 1 and I clear it. All right, a 0, I set it. So you can configure hardware to behave whichever way you like. All right, so that behavior of the register is more of the HDL code that is used to create the processor. All right, so we based on that design, we write the software that writes to the registers. All right. Okay, so demo. Okay, the TA. Okay, so you can demo if your TA allows you to demo in pairs. You can go ahead and demo in pairs. Okay, but you will still have to answer questions individually. Okay, so if you work with your friends, okay, and you want to demonstrate together, that is fine. But your TA will still ask your questions individually to make sure that everybody sort of understands what is happening. Okay, so any other questions? Anything else you all want to clarify? Okay, the clear pending IRQ is not necessary. Okay, the clear pending IRQ is part of legacy code. All right. In the past, in previous designs of the processor or some designs of the processors, you had to manually clear the IRQ request in the NVIC. Okay, but now the latest designs don't need to do that. So you can, the moment the NVIC registers the interrupt and you jump to the interrupt handler, the IRQ request inside the NVIC is already cleared automatically. Okay, so even without that, it's still fine. Okay, but I put it there so that you have a reference that this is how you may see it. If you were to do a search for this online or in other books and so on, you may see this still there. Yes, HDL is okay. So for HDL, there's only two types of languages: Verilog or VHDL. I'm not sure what is being taught here in the module. Okay, but either you use Verilog or VHDL, both of it are equally good. Okay, pushing of register onto stack and all that, that is done by MCU hardware. Okay, so that is the processor's hardware configuration. Yes. Okay, pushing of all that, yes. That is all part of the HDL code as well. Okay, I mean, to maybe to be clear, this, it could vary to some extent to be partially hardware and partially compiler based, but some generic operations like this. Okay, so for example, when a interrupt is registered, there are certain registers that will automatically be saved onto the stack. Okay, so how do I put this? Okay, so for example, when an interrupt occurs in ARM, okay, you will have certain registers that are by default pushed onto the stack. All right, together with, for example, stack pointer, program counter, program status register. All these are by default automatically pushed onto the stack. So these are all done by the MCU hardware. All right. Then of course, you may have some variables that are maybe passed over or things like that. So there can be other parameters that are also pushed onto the stack, maybe inside the ISR and so on. So those are things that are done by the C compiler because of the code you have written. Okay, so certain activities that are by default the standard behavior that should happen, those are taken care of by the hardware. All right, then some of the activities are based on the code that you write. So interrupt handling wise is mostly, I would say, is hardware driven. Okay. Okay, the volatile data type. Volatile data type is basically the case where you have a situation of variables being updated. Okay. Okay, so maybe Let me share this screen right now. All right, so I know it's already 11. So those of you who have a class, you have to go, please carry on. All right, I will just explain this part on volatile. Again, give me a minute. Okay, so I'll just explain the part on volatile. But those who have to go, please carry on. Okay. Okay, the clear pending hierarchy in switch function optional. Yes. Okay, it is. You can say it's optional, but it's a good. Yeah, you can say it's optional because rightfully you would have already been cleared by the end week. Okay, if the interrupt had happened. Okay, so the clear pending IRQs are there just to show you the legacy code. Okay, but these are all optional. Okay, so let me elaborate on the this one. Okay, so imagine that let's say I have a main code here, all right, and inside here I have a variable. Okay, maybe right here. Let's say I have a global variable integer switch. I say if switch is equal to 1, do something here, and else do something here. Okay, and let's say this is written in a while one loop. Okay, so inside this loop, I am continuously trying to check for a switch to be pressed. All right, and then I will decide to do two actions. All right, now if I compile this code, all right, and imagine that let's say the initial value of switch, okay, okay, let's assume the initial value of switch was originally 1. Okay, then if you look at the code here, and there is no part of the code here that actually writes to switch again. Okay, so let me finish this, then I can come to the other questions. So here, if let's say my code here, you can see that there is only a reading. So in here, what I'm doing is I'm doing a read. Correct. So in this entire loop from here to here, there is no writing. There is no write. There is no write to variable switch. So if there's no write to variable switch, okay, you can see that okay, something is wrong in my computer. Okay, let me just explain to you. So in a situation like that, what will happen is when you switch on your compiler, if there's optimization turned on, it will just take the default value of switch to be 1, okay, and it will only execute the if statement, all right, by default, because it will assume that since nobody update the value of switch, there is no way the value of switch can be changed, all right. But if switch was actually a variable that is updated in the ISR, all right, because of compiler optimization, the updated value would not be reflected in the main program. Okay, so that is why you need to have the volatile keyword for such a variable, so that if it is updated even in the ISR, okay, it is still going to be properly read again in the main loop. Okay, so one more question. How do they achieve the behavior where if you just one? Okay, so like I said, this kind of behavior of whether I write a 1, what happens, write a 0, what happens, these are all the processor's hardware design. It's nothing to do with the C programming that we write. Okay, so the processor, when you create a processor call, you are basically you start off with HDL code, okay, to create a processor call. So you write, I mean, I've taught a module before where we create our own processor from scratch. I mean, program counter, ALU, data memory, program memory, everything. So we write everything from scratch, and then we wire up everything, put in all the data, pipelining and everything. So when you're writing HDL code, you can decide how the hardware behaves. So if I write a 1, what should happen. If I write S0, what should happen, and so on. Okay, so if you, okay, to answer that question, okay, the behavior of writing a 1 to the register or 0 to the register is a hardware design. It's nothing to do with the C code that you write. So we just need to understand the hardware design. So we need to read the data sheet and understand, okay, if I write a 1 or write a 0, what happens? Okay, so that is the design. We read the data sheet to understand the design, and we write the C code to achieve the functionality we want. Okay, so if you turn off all compiler optimization, then volatile keyword is pointless. Rightfully, yes, that should be the case. Okay, but compile optimization, again, you need to check carefully. There can be some compiler settings can be quite clear, some may not be so clear. Okay, because in compile optimization, they may have different levels. So if you say optimize for speed, optimize for memory, then they may have speed 1, speed 2, speed 3, memory 1, memory 2, memory 3, and so on. So sometimes those options given to you, okay, for compile optimization may not be so clear on what is actually happening. All right, so unless you're very sure you know what is happening when I toggle these settings, then you can omit the volatile keyword. If not, it is always good practice to use volatile keyword for such shared variables. Okay, so I will end here. I need to reboot this PC. I don't know what's happening. All right, so thank you very much. Okay, I will see you all next week. Okay, for the next lecture. Okay, thank you. Bye.